Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. And for today's show, we've got John Springer with us. He is the segment manager for e-mobility at a fantastic company called Dynapower. Welcome to the show, John.
Oh, thanks, Ryan. Thanks for having me.
No problem. We get started just to find a bit more about you and tell us about your background and how you got involved in doing what you're doing now, please.
Yeah, fantastic. So I've got mostly business experience as a background in business as a Bachelor of Business Administration from the University of Nevada. However, I always had a very strong interest in electronics, electronic design, and kind of through my career, I've been kind of pushed into those types of strategic development, product development initiatives. Kind of starting at a young age, was always very interested in electronics, wiring together my own battery packs, putting things in series and parallel to be able to have mobile CB radios, being able to make my piano keyboard mobile for certain applications. So building motors out of like designs that I would find in books. I'm a little on the older side, so the internet didn't yet quite exist. So this was more like 1970s textbooks.
Some listeners may have to look up what one of those is, but
yeah, exactly. But always like an aptitude for it, and always kind of an interest in electronics. I had mostly have business director level roles, kind of running sales teams. About 15 years ago, kind of was working for what was predominantly office supplies. We were one of the largest importers and distributors. But one of the products that truly captured my interest was honestly the laptop batteries. And being able to kind of provide laptop batteries in large quantities to education institutions and government agencies. And kind of through that got a request from some of the school districts in Texas to learn that the one-to-one laptop programs that they had been rolling out, they had noticed that the battery life wasn't long enough to be able to last through the school day. So was asked to kind of come up with a like high capacity solution in a very short amount of time that was economical. So working kind of with some of our manufacturing partners, we're able to create a design based on an existing laptop battery and provide the additional capacity, which was great. Resulted in a lot of sales, solved a problem. The laptops ran through the day, only to get several months later a call from HP, and I thought this conversation would go completely sideways as a violation of their IP. Was kind of an unexpected phone call, but kind of had learned through the process that they had been able to get their hands on some of the laptop batteries that I had designed and manufactured. And they expressed a similar problem with one of the very early two-in-one computers. As they started performing the actual like testing, their laptop also would not last through an entire school day. And we're looking for a solution faster than what their existing supply chain could support. So went into a development opportunity in producing a high capacity battery for rollout nationally through the third-party channels for an alternative to the existing battery.
That definitely didn't go the way you thought it was going to go.
No. I thought it was gonna be a more conversation like if Apple were to call you up, but this one was far more agreeable, and and it really kind of set my appetite on kind of those real world problems and trying to come about real world solutions. And in sticking with that, moved over to work at a company, PowerSonic, which is a large international manufacturer, predominantly of lead acid batteries, some lithium batteries as well, and had the opportunity to work on additional projects like no idle solutions for trucking, mobile welding applications. And then after working for the company for a couple of years, three of us were brought up from inside of it, and we were asked to create a separate business unit for energy storage to be able to support DC fast charging. So leveraging, our existing customer base and industry knowledge, put together the strategies and product portfolio.
DC fast charging for cars.
Yes,
so we're into
terrestrial.
the EV era here now. So we're, probably quite early-ish on in the EV time. What sort of time period would this have been?
This was just a few years ago, honestly. A lot of the initial installations, as you probably recognize, are kind of the low-hanging fruit areas of adequate grid connection where you can AC couple DC fast chargers. But as you start to look at some of the fleets as they have rolled out their installations, there's an obvious need to be able to support it with both resiliency as well as being able to supplement the interconnection that may be available to them.
Ah, yeah, okay. When they can't get a big enough feed from the main distribution grid to support the number of chargers they want to install.
Exactly. And I know that you probably had previous discussions as it relates to kind of those microgrids and integrations, but depending upon which of the thousands of utilities that you have to work with in the United States, sometimes it's prohibitively difficult to get that upgrade. And in some instances, it's impossible. It's not even a question of, hey, it's going to be 2 or 3 years. It's we're not going to be able to upgrade your service. And my concern is, as it rolls out to some of these fleets, some of these locations end of the line are going to be critical hubs that need to be supported if there's really going to be a true realization of high levels of adoption for EVs at those facilities.
Yeah, we see that problem in Europe as well, and in the UK. It's hard to get a big grid connection in a lot of places, particularly in the south of England. Not so much in the north where I am, but a lot of issues in the south and southeast in particular, where there's a lot of much higher sort of population density. And then, even just for one fast charger, but then if you are like a logistics company and you might be, realistically, we do have logistics companies who are putting 100 vans on the road now, or more, in these quite big rollouts in a one location, and coming up with a way of charging those in one spot is a big topic here, because it then goes, you're talking about megawatts of level of grid connection. So there's some clever things happened with like sharing infrastructure with rail companies and stuff, and but it is still it's a challenge that people are coming up against all the time. So you saw that as a business area, and you were working in the space of those the battery packs. So you're pretty deep at that point in charging and charging infrastructure. Is that kind of how you ended up coming into Dynapower?
Dynapower is a little bit different of an approach. So I was Dynapower, celebrating our 60 years as a company this year, actually, and then acquired by Sensata about a year and a half ago. And for those who don't know, Sensata is a large organization who manufactures a lot of the sensors and technology that go both in terrestrial vehicles as well as other heavy vehicle off-road, marine applications, and a strong emphasis on aerospace. So was brought on board to help kind of define the path forward for Dynapower in the e-mobility market. Dynapower is historically known for high power applications. We do a lot with microgrids, high power. We do military and government work, kind of solving the really difficult challenges, the really hard power electronics challenges that exist in the market. And Dynapower is very well known for its DC to DC technology, which is potentially, well, is a coming topology that will be more frequently used for these megawatt charging applications and some of these larger fleet depots.
Okay, so I didn't realize Dynapower was quite as old as that. So that's like pre-power electronics, power electronics. So
Transformers, yeah,
yeah, old school.
They're very old school.
And now, sort of, I guess, finding a market opening up in all the grid connected infrastructure equipment. Is it, like, just out of interest, in my space, a lot of people kind of we talk about high voltages in electric vehicles, and all the kind of proper power engineers always giggle at the back of the classroom because they're like 800 volts is not high voltage. I'm guessing Dynapower is probably typically in the sort of kilovolt range equipment.
Yeah, it kind of really depends on the application. In the one of the things that Dynapower builds is we build extremely large rectifiers that are the size of small apartments. And these are being used for the electrolysis project, some of the largest international electrolysis projects, which is one of the segments of Dynapower. The other clean energy segments would be microgrids. Dynapower was one of the first in establishing the microgrid dynamic transfer technologies, as well as we also have a focus on renewables and renewables integration. And typically our scope is in the power electronics. But to your point, on the EV side, yeah, when we start talking about high voltage, we're not talking about like high voltage.
Yeah.
So some of the challenges are the like one of the emerging standards in the US, the SAE 3271, is kind of along those higher power megawatt charging standards, and it's up to 1500 volts, 3000 amps is really the target. Which, still thinking about it, is substantial. I mean, if that were a single charger at 4.5 megawatts, that's relatively impressive.
Relatively impressive. I think that's maybe a little bit of an understatement.
Yeah. I don't think you want to plug your car into it, but it does have its place, though. We've been in conversations with large like mining organizations, people that are building really large packs. They're building 1 megawatt hour packs at 1500 volts. And the thing is, there's a high confidence with a lot of these OEM manufacturers in their ability to build a vehicle, but they're certainly not charging experts. So they're oftentimes left with decisions of how are we really going to effectively charge this? How are we going to build out the infrastructure? Do we become a charging company? Do we partner with somebody to kind of enable a one-off solution? Do we sit idly by and wait for the industry to mature, providing a solution? Like, which way do you really want to go in kind of developing the solutions necessary for high power charging?
Yeah, it's interesting that you mentioned mining, and we see quite a lot of activity at the moment around deployment of battery electric into mining, as you know, really significant opportunity. Underground mining, it seems like it's a no-brainer because of the ventilation requirements and stuff for combustion vehicles. So very quickly going to full battery electric, and actually have been for some years. But even the big open pit mines, they seem to be going down that route, and obviously charging those things. imagine like a 200-ton dump truck. That's no small feat. Recently, I was involved with some railway projects. So, again, kind of people putting battery-powered trains into service. And then again, it's sort of very large battery packs up to kind of megawatt-hour size battery packs. So they take some charging if you need to do it even moderately quickly. You need a lot of power available there. So interesting that the output side, you're talking about up to 1,500 volts. It's sort of 6,000 amps or 600 amps.
Oh, 3,000 amps. 3,000 amps. That's
just that much.
I mean, power. But.
Yeah. On the input side, do these things connect directly into like the medium voltage grid, or are they on some sort of localized power system?
So that's kind of what we're looking towards in kind of the new topologies, because currently you would take a look at it and it'd be AC coupled as kind of as needing to build basically a substation to be able to support that level of charging. But one of the like we're Dynapower is involved with, and I'm involved with EVs at Scale, which is a national labs consortium. And really, the outcome is a DC coupled charging architecture that's of much higher efficiency, as well as the development of the power electronics that are necessary to be able to charge at those outputs. When you look at kind of what exists for like DC to DC converter technology today, most of the level 3 chargers are built out of smaller building blocks, 30 kilowatt modules, 60 kilowatt modules. And if you can imagine how many you have to parallel to be able to get to these megawatt charging standards, it starts to become ridiculous numbers of converters. One of the products that we sell, and it's somewhat unique to the market, is a larger format DC to DC converter. So we have a 500 kilowatt DC to DC converter. We have a 1,000 kilowatt version coming out at the end of the year. And it runs voltages anywhere between an input of 100 to 1,500 volts, and it's symmetrical with an output of 100 to 1,500 volts. So interestingly, it's used really for solar plus storage, for DC coupled solar plus storage, but it's got a high amount of interest in the EV field, since it's one of the few items that sort of builds to that standard, that emerging megawatt standard. It checks a lot of the boxes kind of right off the top. So as far as testbed activities, rail charging, marine charging, yeah, it's something that's getting used for those types of high power charging applications. But it has a limitation in the fact that galvanic isolation and isolation isn't required in solar applications, but as it relates to EV charging applications, it certainly does. So it's really kind of the development of isolated DC to DC technology is a building block for some of these larger high power charging applications.
Interesting. Lots of interesting things going on there. So leaping out of that, for me, the question, just to sort of expand on a bit, what is it that you mean when you say this DC coupled charger topology? I think people will be familiar with like DC fast charging, but I know that's not what you mean. So can you expand on that a bit for me?
Yeah, certainly. So in the installations today, inside of the charging hubs themselves are the conversions from AC to DC. This shifts the AC to DC from the hub components to a single point of grid connection. So there's only the one-step conversion to a common DC bus. Within that allows the integration of a more logical integration of renewables, higher efficiencies. So if you take a look at wanting to integrate battery energy storage, solar, hydrogen fuel cells, and being able to generate a common DC bus, utilizing high power electronics where everything sits within the DC without multiple stages of AC to DC conversion.
Okay. So if we had a site, let's say we have 5 DC fast chargers that everyone's sort of familiar with, they are sitting, and behind them somewhere, we've got a big AC to DC converter bringing the power in from the grid and putting it into DC. But then we can drop onto that DC system a battery pack or other like direct solar inputs you mentioned, I think. So
Yeah, we can integrate the solar. Exactly. So being able to seamlessly integrate all through DC, yeah, all of those assets, and then the charger itself, not taking it like an AC 480 feed, but rather a like 1,000 volts, or as you build towards the megawatt scale on a 1,500 volt bus, directly into the charging unit itself. So it stays DC to DC the entire time, as it would flow through the dispenser into the vehicle, whatever it is you're aiming to charge.
and that really, so you use the word dispenser there, which is that's effectively simplifying the bit of hardware that you would see at the vehicle. Is it simplifying? Yeah, I guess it's simpler than.
So, yeah, simplified sounds good. Yeah, it sounds good to me. I'll go with it. But yeah, it would be a much like a reduction in the size of the dispensers. It's typically just acting as a pass through for the power electronics, which aren't necessarily located right at the dispenser site itself.
I think some companies are kind of moving towards this kind of topology for the bigger charger parks now, and you do see it. The positive is I think they can load balance, so you can have smaller grid connections and smaller AC to DC and stuff sitting at that side. But the negative is if the charger park is completely full, which doesn't happen that often, but if it is, then you can't have full power at every single charger. That's normally kind of sized off a little bit. Is that kind of about right?
Yeah, like in a sense, when you look at it, you can size the interconnection more appropriately towards the average than the maximum. So what you're looking to do is really charge the EVs as soon as possible and as fast as possible is really kind of the aim. The inverters first. If the EV load were to exceed the inverter, if it's not enough, then you would use the battery energy storage to supplement it. And then if neither is enough, then you do have to take a look at energy management strategies, potentially lowering the overall output of the system to be able to accommodate all of the vehicles. But one of the things that the more intelligent site energy management software looks at today, or will look at more so in the future, are those algorithms of what really is the dwell time? What really is the required energy requirements for the vehicle? How do you prioritize what's coming in, what's going out? And if you're within a DC architecture, you do also have, through kind of the emerging standards, the ability to power share amongst the other vehicles. So if everything's plugged into a common DC bus and something's going to sit idle for a while, that power and capacity can be reorganized into providing it to the most appropriate vehicle.
Yeah. I guess as you were sort of saying it there, I was thinking, yeah, actually, if you had 5 or even 10, and it was busy, the busier it is, the more time you've got sort of, putting vehicles on, putting vehicles off, plugging, unplugging. So there is actually quite a significant amount of the time in the charge cycle where the charge is not being maxed out, and it can't be, it could be because of the battery sort of charge profile or just physically someone having to pull up to it and plug into it and stuff. So managing that traffic flow through the park, I can really see you could optimize the structure of the power electronics on the site to, and by that we mean make it more affordable. So
Exactly. And looking at it kind of as more generating like a standardized topology, standardized products and offerings, where each one of these large fleet installations doesn't necessarily need to become its own science experiment. in a way where you do start to see that industry standardization, the ability to take components and fewer components and being able to scale to what it is that you need today, and a quicker path to augment a site for what potentially you might need tomorrow.
And so you mentioned you've been involved in a big project looking at next generation charging and things like that. Where is that project at now? Is it just kind of getting going, or is it up and running? Can you tell us more about that?
Yeah, Dynapower has done some larger with partnerships, some large fleet installations. One of them being the Brookville Bus Depot in Maryland, where we provided the power electronics and energy storage, and worked with partners to be able to build a large bus charging depot integrating solar, eventually for hydrogen production, potentially for hydrogen fuel cell. But this system is again coupled on the AC side with AC fast chargers, not any of the kind of sort like emerging currently, the DC coupled chargers. And interestingly, I have a lot of conversations with a lot of companies all the time, and it's funny because like I'm a firm believer and nobody really has like an original idea. There's 8 billion people on the planet. Somebody's probably thought of it first. So as it kind of reaches like a certain point, you start to see it more and more frequently. So a lot of the conversations that I've been having with OEMs, with site developers, other stakeholders in the industry, the DC coupled topology is definitely rolling forward, and it will be a emerging topology that I think you're going to see a lot more frequently, especially when you take a look at kind of the larger fleet and megawatt charging requirements.
Yeah. What's holding it back, today? What needs to happen for that to really accelerate? Is it hardware? Is it just the installations aren't going in yet? What are we going to see?
Yeah, I think that like much of it still has to do with kind of being able to, as it relates to chasing like the NEVI funds and kind of finding the low-hanging fruit, the areas where there is adequate interconnection, where there isn't as much distribution congestion. As you start to run out of those sites, then you have to start taking a look at other solutions to be able to provide that on-site generation or be able to work with a smaller interconnection. You'll start to see this DC coupled topology occurring more frequently in those instances where you can't just take a standard 480 connection and plug it into a fast charger. But for like the requirements for the technology, there's considerations to be made for the hardware development, the communications protocols, working with site energy management software companies to be able to utilize it on a DC bus. There's questions about DC protection schemes, which are different than AC protection schemes, and ensuring that these sites are safe. But it's a very, very strong push forward from both the industry as a whole, as well as kind of Department of Energy initiatives, and really seeing this brought to fruition. There's just too many upsides to it in terms of efficiency, cost reduction, the ability to put really any DC based asset on the bus much more efficiently than trying to build everything through different stages of conversion.
Is this going to be just how charger parks are in the future, or is it more likely that it would be what we'd see in a commercial vehicle installation, and actually a passenger car charger park would look somewhat different?
Yeah, there's the right solution for everything. So it's not like AC coupled solutions are really going to go anywhere. If you have like a large park and you want to put in a lot of level 2 chargers and you have the existing AC interconnection, there's no reason to not necessarily couple that type of a solution on the AC side. When it gets into kind of you're wanting to provide all of those DC generating assets all at a single location and wanting to have much larger fleets, then the questions of efficiency and ability to integrate that on-site generation is important. And I personally feel that on-site generation is going to have to take some leaps and bounds forward, just to accelerate the process of interconnection and be able to provide at those points of use the power that would be required. But you can't always think of it in terms of having adequate solar. I mean, if you take a look at like the amount of solar you may potentially require for some of these large developer charging locations, you don't own the 50 to 100 adjacent acres, and you certainly aren't going to be even potentially able to purchase it. I mean, like you take a look at California. You're not necessarily going to buy the next 100 acres next to your site. So what sort of generation assets can you potentially put on a site to kind of augment its capabilities? And it's a combination of things. It's a combination of what you can get that's available today, what will be coming in the future, how best can you integrate the renewables? Do you want to maybe integrate like hydrogen fuel cells as kind of a smaller format, yet ability to be able to kind of provide that base load power?
Do you think most sites are going to end up having a bit of on-site battery storage then, as we move forwards? The actually batteries are going to be a big part of that infrastructure, because you can get a bit of solar on site, and if you have a factory or something, you can get it solar on the roof. But do you think actually the real answer, or another answer, is just using that smaller grid connection and kind of trickle charging a buffer battery pack? Is that going to become what we see as a standard?
Yeah, I think that in at least the midterm, the integration of the batteries on site is a positive way to take a look at what you have available and then being able to supplement it with the energy storage. It helps to reduce the demand charges or the peak draw to the site itself. Kind of moderates that. Depending upon the location, you can shift time of use. So you can collect the energy at the lowest point of use and then dispense it when it's most expensive during the day. Or in other instances where people take a look at the like school bus situation and the ability to potentially monetize your fleet using DER solutions, selling back the energy from the grid. Now, that's one of the few instances in which, like, I think that business model works. When we're speaking with fleet operators, they want to charge their vehicles, not necessarily participate in grid support services. Like, that might be down the road, and the batteries will certainly help support that. But when they take a look at it, first, they're a logistics company, but maybe they do need to start taking a look at themselves as an energy company as well.
Yeah, it's an interesting one. The US school bus is a sort of special. We don't have anything like that in Europe. They'd use the public buses typically, or kind of charter in buses that then spend the rest of the day doing other work to do the school duties. So there's kind of big fleets that you have in the US of buses that are then kind of idle most of the day, and have two peaks. It's not something that we have in Europe. I think in some parts of Asia they have similar, where they're shipping high densities of workers in and out of industrial areas and factories and things. But I think the load factor here, the vehicles are moving basically, and the problem is that they don't stood still for long enough. So
exactly, and that's the case of most of that's always been built down to a science, is like, how can I keep my fleet moving and operating? And that's why some of the high power applications are so important, is to reduce dwell time. If you take a look at like the mining scenario again, um, if that truck is down for an hour, I mean, what's that really costing in terms of revenue? So the ability to fuel that vehicle, to charge that vehicle, is of importance. And with the school buses in the U.S., honestly, that fleet sits idle through the summer. So you have these the battery assets that are literally sitting there for months, available for grid support services. But in kind of my experience in talking to different corporations, different ways of realizing this, that seems to be kind of an interesting outlier. It's interesting that many of the RFPs that are being released do have a component for vehicle to grid services as part of the requirement. So it's not as if it's just it's kind of compulsory in the sense that like it's a requirement. It's not necessarily like a choice sometimes.
I think, I mean, not so much for vehicle charging, but one application I have heard about a few times, which is quite an interesting one from an energy storage point of view. You know, a lot of buildings require backup power systems. So, you know, they might have a backup generating set or some sort of big UPS. And I have heard of a company who effectively are doing like a managed UPS service using batteries. And part of the business model they have is that they also provide grid support, you know, fast frequency response type services with those installed systems. So I think, you know, like a hospital or any building with a backup power supply, which particularly in the US is quite a lot of them. You've got some installed capacity potential there, which you could use for other purposes, you know, like supporting charging and buffering the grid for stuff. So when you start to think about buildings and in a more kind of joined up way, that kind of energy system, all of a sudden there's lots of possibilities for the things that you can do in amongst all of that.
Yeah, absolutely agreed. And I think that is a positive use of being able to support the grid, provide that resilience, that safety that comes with having those distributed resources, which are more localized in terms of if there's an outage or if there's a problem, and the ability to monetize your asset. So instead of it just sitting idly by, there is an opportunity to both support the grid as well as those economic considerations. One of the other interesting scenarios is in mitigating demand charges and time of use rates, even at smaller like NEVI size charging locations. If you were to put battery energy storage at those locations to help mitigate the demand charges, yet also aggregate all of those assets as a collective, then you could use the aggregated assets as an economic dispatch as well, even using smaller battery systems.
Yeah, I do. I mean, I wonder, as we start to see more and more of that, like just from a personal perspective, I fitted solar and battery in my home, so residential system. The battery side of it actually is a no-brainer. So we don't use peak electricity basically anymore. You know, even if we don't have enough solar. I live in the north of England, so we're not exactly blessed with a lot of solar. Not like California, but we've got a bit. But it really is the battery side of it and shifting our demand into that 3 or 4 hours of off-peak between 12:30 and 4:30 in the morning. That's when we put all of our consumption through and I wonder how much of an because obviously if everyone's doing that, then that becomes not the point at which it's no demand. So it'd be interesting to see what starts to happen in terms of people being able to shift that demand point around. And then the other thing is then what does that mean for the grid? You know, I mean we've the solar and battery system we've put on our residential property, we've absolutely slashed our energy costs, which is great because it means we've got these assets and they're doing their job for us. But it then means that we're not kind of making that contribution back into the grid and centralized generation. And you do wonder if a lot of people start to shift to more decentralized power, particularly industrial commercial users, what kind of impacts that's going to start to have on the grid and more like centralized power generators. I don't know if you have any thoughts on that. Are you starting to see things like that happen?
Actually, I do have some thoughts on that. That very closely mirrors one of my good friends' perspectives. So one of my good friends is the director of transmission planning for NV Energy, so the utility here in Nevada, and it does closely mirror that as you put these storage and generation assets on your property. You're still interacting with the grid. You're not an off-grid system, so you still are a customer in terms of their needing to support, upgrade infrastructure, provide your point of connection. And then what happens is a trade-off to the other people that don't necessarily have that capability yet at their house. And does there become a tipping point where how do you choose to support the infrastructure if everybody's bill is netting out to $0?
Yeah, it's not commercially. It's not very good for the network operator.
Yeah, no, it's not. And then in the U.S., it's a lot of the infrastructure build out. There's a lot of talk of being proactive in developing the infrastructure necessary. But it's kind of been my experience that really they wait on interconnection applications before building it out. And you have to say who's really going to foot the bill, who's really going to be the off taker of the infrastructure upgrades, who is going to pay for it, and where do you put it? And like you can run it predictively, but without hard world data, it's hard to necessarily justify that business decision for a utility. Now, they want to put in the additional infrastructure, but they need assurances that like once they've made those upgrades, that there's going to be a customer at the end of the line.
I mean, do you think in general, the case study or the history of Dynapower as a company, you've gone from like transformer-based technology to active power electronics technology. Do you think it's getting less expensive or more sort of expensive to do grid scale development now, because we've got a lot more technology than we ever had, solid state stuff at a grid level, so grid voltages or even regional, local medium voltage systems. Is that helping, or is it actually it's just all more expensive and more complicated than it used to be?
In terms of the economics for it, as it relates to more or less expensive, I think a lot of it just ends up being just prohibitively difficult to achieve in terms of correcting the distribution congestion that exists in the United States itself. Is what really does the infrastructure upgrades look like in terms of upgrading the entire infrastructure to be able to support having renewables put onto the grid, having the distribution level service available when you need it, and how long does that take? Applications take quite a long time to be able to go through. And when you look at having the amount of infrastructure upgrades just in general that are going to be required in the U.S., I mean, you're starting to look at, and I mean, don't quote me on this. This isn't McKinsey numbers, but like it's $1 trillion problem. This isn't going to be solved by like a few $1 billion. I mean, and it has to be solved in such a radically short period of time that really taking a look at what you can do in terms of batteries and distributed energy resources is important, because the overall upgrade to the infrastructure, I think, is going to be out quite a bit further than some people might anticipate.
Does seem like the more distributed systems provide that kind of speed element that, I mean, particularly if you're looking at building a new nuclear plant or something like that, I mean, that's a decades-long project, isn't it? It's sort of the scale of rollout of and more of nuclear, which is there's interesting work happening on that in the UK, particularly with small reactors and things, but that's decades away from being in service.
Yeah, I agree, and I have my feelings on the subject and don't necessarily always interject because I don't want to be pointed out as the crazy person when it comes to nuclear generation. But when a small footprint, something that provides baseload power, doesn't rely on the wind, doesn't rely on the sun, and can have that continuing output without having to own the adjacent 100 acres, is an attractive solution. And some of those containerized solutions have a lot of fail safes in them. They don't go over like 500 or 600 degrees. It's difficult to push something like that into runaway. But you're right in like the legislation, and then just the consumer appetite for that dirty word of technology. I wonder how far out it really is, but in the need to really like correct realistic generation sources in a smaller footprint, I still would table it as an idea for sure.
I think the advantage that we have in the UK, US, some parts of Europe, not all parts of Europe, is that there's some existing plants, and you can kind of more easily get permission to build something new in an existing plant. So if you can add capacity, small footprint stuff inside existing sort of designated areas, that's quite doable. But getting permission for new stuff is just almost impossible. I mean, even in the UK at the moment, I was reading in the news yesterday about there's been a push to try and get more energy from waste plants, which when you call it an energy from waste plant sounds nice, but when you call it a waste incinerator that generates energy, it doesn't sound so nice. And they're having huge problems getting planning permission to put even one up. You know, it's seems like a no-brainer in terms of solving two problems, but people just don't want them.
It does. It just has that negative connotation, which makes it difficult. Like I've looked into waste to energy in the past, and in a lot of instances, it seems like a pretty viable solution in being able to have a reasonable feedstock, be able to sequester the output in terms of being able to not just generate electricity, but it also generates like hot water. There are like other pluses to it. And then the water component, potentially you could figure out a way of integrating it with like hydrogen electrolysis or something like that. I mean, there's a lot of options kind of available for it, but it does kind of have that social stigma, which I think makes it more difficult to have an uptake.
Yeah. Even that, food waste energy, which is sort of one less, so anaerobic digestion plants, is pretty difficult to get permission for those as well. People don't like them either. So it's kind of, this is very hard to keep everyone happy. So just kind of wondering, maybe like diving slightly back towards your technology side of things. I was aware, or have been aware of, there's some really interesting stuff happened with power electronics technology for higher voltage applications in the last couple of years, and my friends and colleagues who know much more about it than me tell me there's some really interesting things coming with like gallium nitride switching devices and higher voltage silicon carbide switching devices and stuff, making effectively things possible for high voltage, high power electronics that were not possible even a couple of years ago. Are you seeing that change your business at Dynapower, and how quickly are you seeing new technology come through that's going to really start to change what your power converters look like?
Yeah, I really can only speak honestly to like the product developments that I'm intimately involved with. On our renewable side, there is certainly talk of high transmission DC to DC as opposed to the AC propagation. But for what we really need in terms of e-mobility, the silicon carbide, IGBT, that it's an existing technology which it can be integrated into what's needed, at least in the foreseeable future, without having to creep into incredibly high voltages or higher voltages where it may be a ways off. Like we've been asked to achieve like 5,000 volts kind of on the input side of things on a larger bus, but in terms of like economics, one of the considerations is also is what's economically feasible. When you want to roll out these like fleets and depots and working with emerging technologies, you also want to ensure that I think you want to meet like those economic targets. So everything pencils, so what can be achieved realistically is important as you develop a roadmap for the future. But some of this DC coupled technology and what we need to develop in terms of the power electronics can be done now. It doesn't necessarily rely on like a future technology.
Okay, cool. Looking ahead, so like what have you got coming up the next kind of year or two that you're most excited about? What's your outlook on the future?
Yeah. So it's really moving more towards the high power charging applications and being able to take a look at it, not necessarily in just terms of terrestrial vehicles, but our ownership by Sensata also provides the ability to work in other markets as it relates to high power marine charging applications, starting the conversations with the electric aircraft manufacturers, heavy vehicles, mining equipment, and really kind of staying in what Dynapower is really known to do, which is solving complicated problems with higher power solutions. The 60-year legacy of being able to achieve this for many partners over the years. So really kind of looking towards those high power applications and really looking to help develop the DC coupled topologies for some of these fleet installations, as well as it relates to like the marine and aerospace markets as well.
So we look forward to seeing and hearing more from you guys in the future, and it's going to be really interesting to follow the business. But thank you very much for taking the time out today to talk to us, John. It's been an absolute pleasure to have you on the show.
Ryan, thanks for having me. This has been a blast.
Brilliant.